Here we go. Oh yeah, we're gonna do this in pencil. All right, add a lead there. See if we can swing this. There we go. Okay, so we've got just looking for the absolute minimum, absolute max. So when you do something like that, you want to create a table. They're not asking for increasing, decreasing. So what we can do is just kind of like make a table of our values. We know that pi over 2 is here and 3 pi over 2. And I do remember that there was only one value that was in the middle of these two that actually equaled 0. Just because we did this earlier. So I just made a table of 3, but you know, it might be 4 or 5. It just depends on the function. What we need to do is just set this this derivative equal to 0. So we will get negative 3 sine x. And then when we set it equal to 0, that will tell us that's where absolute mins and maxes, well, relative mins and maxes happen. But absolutes can also happen here. So let's find out where that point is. And the only place where sine of x will equal 0, once I divide both sides by negative 3, is going to be pi. So x equals pi. So pi is the one critical number that we have inside this domain. Okay, now when I plug pi over 2 into the original function, I will get 0. And if I plug this guy into the original function, I will also get 0. But if I put pi into the original function, I'm actually going to get negative 3. So it looks like we have an absolute minimum of negative 3 and a max at 0. And that is sufficient. If, for whatever reason, we need to specify where exactly that happens, we can write this just to for clarity. Okay, but this does answer the question. Okay, so now we are in a spot where we have the second derivative and the critical values are here. So we want to use the second derivative test to determine which critical numbers, if any, give a relative max. Okay, so relative maxes happen when things are concave down. Okay, so in order for concave down to happen, because the max happens right there, we want the second derivative to be equal to less than 0. We need it negative. So since they already figured out where our critical values are for us, we just plug these three numbers into here to actually see what we get. Okay, but we are looking for the negative version. So we're going to plug in negative 1, we're going to plug in 0, and we're going to plug in f double prime of positive 1. Okay, if we plug in a negative 1 into this guy, we are going to get a negative 2. Okay, so that right there is a concave down. So we know that this guy is going to give us a relative maximum at x equals negative 1. So which critical numbers will determine if it'll give us a max? Well, right now, relative max, okay, is at x equals negative 1 for now. Let's check, pull in a 0, and we get 0. Okay, so in this actually the test fails. This is where a point of inflection would happen. Here, if I plugged in a 1, I'm going to get a positive 2, and that would give us a concave up. So this means that this guy would be a relative. Now remember, I only know it's a relative min because it told me that those were critical numbers. Okay, otherwise it would just be normally concave up, but it's a min because that is a critical number. Okay, so relative min there at x equals, but that's not what they asked. I do believe they just asked for the relative maximum. Okay, so here the, what is that, positive 2? Okay, positive 2, but this is the guy that we want. Okay, happens at negative 1. What do we plug it into? Like, what is the maximum value? We don't know. We don't have the original function. Okay, and these could be the critical numbers of any function. Okay, so now determine whether or not. Okay, well, we already said that this guy has. There is infinite discontinuity. Or you could just say not continuous from 1 to 4, so the MVT will not apply. Over here, though, this is a line in a trig function, so that's going to be nice and smooth, no division of 0. So we're going from 0 to 2. So what we need to do, though, is find what the average rate of change is. So the AROC is going to be, first of all, 2 pi minus 0, and then we're going to plug in 2 pi into this one. So that'll be, because remember we're doing f of 2 pi minus f of 0. That's what's going to go right here on the top. Okay, so 2 pi cancels out, you get pi, and then this is, the cosine of 2 pi is actually 1, right? Isn't it 1? Yeah. Okay. So that would be plus 1. Okay, and then okay, we are having issues with my hover cam, so man, I hope I can get these done. Okay, so this was the 2 pi, and then we're going to subtract 0. Plugging in 0, you get 0, and that's 1. So you can see that the 1's do cancel out. So you get pi over 2 pi, which is just 1/2. Okay, now that is the AROC. Okay, so this means that from endpoint to endpoint, I have a slope of 1 over 2. Okay, now somewhere along here, there is got to be a tangent line that actually has the same slope as 1/2. So what I've got to do is figure out what the derivative is. Okay, 1/2 minus sine of x. Okay, and what I've got to do is I've got to figure out what value of c is going to give me. Whoops. What value of c is going to give me 1/2. Okay. Okay. So now I'm going to subtract 1/2 from both sides. I get 0 equals negative sine c. Take the we'll divide by -1. You get 0. The only place where sine is 0 from 0 to 2 pi is actually at pi. So c equals pi. So that's it. That is the only location where this guy actually is going to equal. Now you can't include the endpoints. That's actually where the mean value theorem has to be applied to a closed interval, but you can't. You don't need to plug in those points because you can't take the instantaneous velocity at that point. Okay. So here, find the open intervals where this guy is increasing or decreasing, and find all relative extrema. Okay, so let's find out. Probably be better to actually do this on a separate sheet of paper, but if I want increasing or decreasing along an interval, that is absolutely the derivative. Okay, and so there's our derivative. I'm going to factor out a 3 here, I notice. Okay, and then I continually factor there, and I'm going to get x minus 4 and then x plus 2. So this means then that where it equals 0, okay, so -2 and 4, okay, where that equals 0 is where we're going to get the critical points. Okay, so let's find out then. Let's pick a number to the left of -2, say -3. -3, we plug it into the derivative to see if it's negative or positive. Don't plug it into the original function. This guy is just going to tell you how high your graph is, but it doesn't tell you if you're increasing, okay? So, or decreasing. So let's plug in a -3, and that's going to give us negative. So together, when I multiply them, it would turn out a positive. Then in between here is 0. That would give me negative, and that would give me positive when I plug it in. So that's a negative. And then a 5 is going to give me 2 positives when I plug it in. It's really nice when they're factored because you don't even need the actual number. You just need to know the sign. Okay. Okay, so it looks like this guy is increasing from -infinity to -2 and from 4 to -infinity. All right, and then the minimum point. Okay. Well, here, let's just do the decreasing because that's kind of easy real quick. It's in between those two. Okay, so this guy's increasing, then he decreases, and then he increases. So the minimum point happens right here at 4. Okay, it happens at x equals 4. So when we plug in a 4, we are actually going to get 72, I believe, negative 72. Okay, it does say point, so we do have to give the x and y coordinate. Here, the maximum happens at negative 2, so when you plug in a negative 2, just use your calculator there, you should get 36. Okay, and that's it. That's it. Okay, moving forward with this guy, we've got find the open intervals in which the function is increasing, decreasing, okay, just like this, but now we're going to do concave up and concave down as well. And we're also going to find the point of inflection. So we need both the first and the second. So let's go ahead and take the first derivative, 3x squared minus 8, and let's set that equal to 0. Okay, get our critical numbers. And this is going to be weird, but we're going to have to move the 8 over there, divide by 3, take square root, and we get this nasty plus or minus radical 8 over 3. So here we are with the positive 8 over 3, and here we are with the negative 8, radical 8 over 3. Okay, so these guys are kind of like our borders, and what we've got to do is figure out what happens to this guy when we are less than that particular number. Now, I don't know what that number is, but I'm pretty sure that 8 divided, well, let's see if we can estimate it. 8 divided by 3 is a little less than 3. Taking a square root of a little less is going to be 1 point something. So I'm just going to go negative 2. Negative 2 up here will give me a positive value. So this means that this guy is positive. Okay. Then in between, if I pick 0 is like right there in the middle. So if I plug in a 0, I will get a negative 8. So that's going to be negative. And then I betcha if I go on the other side, let's just pick 5. Okay, that's 75 minus 8 is going to be positive. There we go. Okay, so this is the first derivative. So we can say that increasing goes from negative infinity to negative radical 8 over 3. Then he takes up the mantle again for increasing on the other side of radical 8 divided by 3 and goes all the way to positive infinity. It is decreasing in between these guys, so it's weird to kind of write this number so much. He's just an irrational number. No harm in that. Okay, but what we can say is that this guy increases, then he decreases, and then he increases again. All right, so where is this guy concave up? Well, it looks like he is concave up right here. Okay, but let's find out where he switches gears. Okay. So for that, we go to the second derivative. Okay, so let's take the second derivative, and that's just going to be 6x. So making that equal to 0, we're going to get x equals 0. So right there is 0. So right there is the point of inflection. So this means that if I go to the negative side, my second derivative will give me a negative. And over here, this will give me a positive. Okay, I'm plugging it into the second derivative. So this means then that this guy is concave, and you can kind of see by the arrows, right? Okay, it's concave positive up, and then concave down here. And it's right at 0 is where it switches gears. Okay, so our point of inflection is right there at 0. Okay, so that's one question we can answer pretty quickly, even though we should save it for last. And if we plug in a 0 here, point of inflection is at 0, 0. It is concave up from 0 going all the way to infinity, and it's concave down from negative infinity all the way to 0. Then at 0, 0, it has a point of inflection. The relative minimum is going to be the lowest possible value, and that has to be at positive radical 8 over 3. Now, I don't know what that is, okay? But you've got to plug that guy into this guy right here. Okay, and when you plug it in, you're going to get around negative 8.709. Okay, and that's at x equals radical 8 over 3. When you plug in the positive version in here, you're going to get around, oh my god, positive 8.709. Now that's not guaranteed that they're going to be symmetrical like that, but in this case it is. Okay, all right, that is the first page.